Welcome back. Let's do another Thevenin equivalent. And this time we're going to do some different methodology here. So there's still two steps to this. One, you're going to find V sub Thevenin, and here we're going to use node voltage. But the second process that you do for these problems is you solve for R sub Thevenin as a kind of a separate problem. And here we're going to use the test source method. All right. That's what we're gonna do. So this is kind of a fun little problem here given this circuit right here. So we have a dependent source on this guy, so that's why we have to use the test source method basically. When you have a dependent source, you have two choices. You have test source method, or you can use the short circuit method. Here we're going to use test source. All right, that's what we're going to do. So there's a resistor here, then there's a current source and a voltage source. Got a little squished. And here's our terminals of interest A, B that we want to find V sub Thevenin with respect to. So I'm just going to leave this guy alone. That's our original circuit, and I'm going to take the time to redraw him or her. So yeah, there's our circuit. So we've got a 4 amp current source, a 24 volt voltage source, and these are independent sources. And then I've got a dependent source, 3ix, and this guy needs to have a reference volt current, ix. So here's ix right here. So whatever current is traveling through this little branch right here, this guy will multiply that times 3 and put it out that way to the left. Okay, so there's two steps to this. One is V sub Thevenin, and we're going to use node voltage, although there are other methods you could use. So I'm going to go ahead and redraw the circuit here, for node voltage, just because process 2 for our Thevenin, you want to start over with the original circuit. So I don't want to mess up the original circuit by drawing all over it. Okay, we'll throw our nodes on here. So this is 0 volts. Maybe I should finish labeling stuff, huh? 3ix, 8 ohms, ix, the reference current that this dependent device is using. All right, so if this is 0 volts, then we have 0 volts at terminal B, and we know that we have V sub Thevenin at terminal A, because that's what we're trying to find, is the voltage across AB. So if it's 0 volts down here, then it's V sub Thevenin up here. This node here is also V sub Thevenin because there's no device in between these two guys. I like to draw a big fat node, big long old node. I like that. Okay, so we're going to do node voltage. So node voltage, you're summing the currents. Just to review the methods, you're summing the currents at a node. Let's use in will be negative and out will be positive. And those terms that you're summing are going to be I terms and V over R terms. So node voltage at, let's do V sub Thevenin. Write a node voltage equation at this terminal right here, so at this node right here, which is also terminal A. So we have ix coming out, we have 4 amps coming out, we have 3ix coming out, and then I got to choose whether the current is coming in or out here. It's not given, and it's not so obvious which direction this guy's going. So we'll choose, let's just choose that way. And that's just really pretty much a total guess. But if I chose that direction, then I need a V over R expression for this current. So I need to know the voltage here. And I happen to know that because it's 0 volts down here and it's rising 24 volts. So this node has 24 volts on it. Okay, so I can write all of these currents. So let's see. So I've got, I need another pointy device here. I've got 4 amps coming out, so that's 4. I've got IX coming out, and I could use IX, but look, IX is V Thevenin over 8. And that'll reduce one variable, so I can keep it down to one equation if I do that. So yeah, but you know, I'm still going to have this. Let's just go ahead and stick with IX. So I've got IX coming out here. I've also got 3IX coming out here. I've got 4 amps coming in. I've got IX coming out. I've got 3IX coming out. And that's it, right? No, I've got this guy. I've got this guy coming in, which is the potential difference. So it's 24 minus V sub Thevenin, the potential difference over 2 ohms. And that's coming in, so that's negative. All right, that's the equation right there. So now I can plug in this IX to get rid of one more variable. So this becomes, well, let's combine these two terms. So this is 4, and then IX is V sub Thevenin over 8. Okay, minus 24 minus V sub Thevenin over 2, it'll sum to 0. And then, you know, just to save some time, you know, if you crunch this, and you're going to get V sub Thevenin equals 8. All right, that was step 1. Or process 1, you might want to call it. It's a little bit more than a step, I guess. But this was process 1 to calculate V sub Thevenin. And then the method we used for process 1 is node voltage. All right, process 2, we're going to try and find R sub Thevenin. We're not just going to try, we're going to do it. And so here we want test source method, just for something different to do. Actually, we have to use either test source method or short circuit method because we have one of these diamonds. Those are the rules. I don't want to talk about why the rules work because that just wanders off too much. At some point, you need to just use the rules. You know, the book talks about the derivation of the rules, and that's good stuff, but my main focus is just using the rules here. So for test source method, what you do is you still open the I's and short the V's. You still do that, but R sub Thevenin is going to be given by V sub test over I sub test. So you're going to insert a test voltage into the original circuit. So that's why I took the time to redraw this circuit for node voltage method, because we want to start over with the original circuit here. So I'm going to start over with the original circuit and insert a test device. Okay, there's our original circuit, and what we're doing here is across terminals A and B, we're inserting a test voltage, V sub test. And that test voltage is going to have a current associated with it called I sub test, right? Okay, so we started out with an open circuit across AB, at least in terms of in terms of the Thevenin equivalent. We're looking at this as an open circuit. And now we're kind of closing that up by attaching a test device. Now if we do that, then what happens is, oh, I forgot to open the I's and short the V's, didn't I? Yes, I sure did. You know what? I'm just going to start over right here on this. I'm just going to redo it, okay? Because, you know, I could scribble all over it and make it look good, but, you know, that's no good. So we're going to open the I's and short the V's. So that was a V I just shorted. This 24 volt right here. Oh, it's in the wrong place. Hey, let's go one more time, huh? It's only paper. Plenty of trees. There's too many trees, I think. No. You can't have too many trees. Down here he is. He's there, right? That was the 24 volt that I'm shorting. We're using test source. This is step 2. We're trying to find R sub Thevenin via test source, which means we open the I's and we short the V's and we solve for R sub Thevenin equals V sub test over I sub test. I sub test. V sub test over I sub test. Okay, so this becomes open. It's kind of messed up one more time, but this guy is open. It's an I. It's a current source, an I. So you open it. So I didn't mean to draw this wire right there, but you open that I and you short this V. Okay, I sub X is still here. This is node A. This is node B. Don't forget V sub test. And its associated I sub test. All right, I think I got it. So I took the original circuit for process 2 here. I took the original circuit and attached a test source. And you do that, you attach a test source, which is going to have V sub test and I sub test. And then you do this open I short this V's for the circles, that is for the dependent voltage and current sources. You do that. So I shorted this voltage source and I opened this current source and I end up with something that looks like this. So it's a whole kind of separate problem. You start back with the original circuit. All right? Then what we need to do is we need to find an expression for Vt over It, because that will give us R sub Thevenin. Presented without evidence, that's just the way the method works. Okay, and there's a nice derivation in the text about why this works, but for us, we're just going to apply this method right here. So what you need to do is look around and see where you can get an expression for Vt over It. You just kind of have to look around. And so you look, and it turns out that if you sum the currents, I'm just going to say turns out that the sum of the currents at node A works. So this is node A. This is also node A. All across the top is node A, you know, because there's no devices in there. And I've drawn I sub t kind of going through node A. I mean, really, you could scoot it down here if you want. This is I sub t. If it's confusing, drawing it on the node, draw it coming into the node. So we'll have. So basically, in is going to be positive and out is going to be negative. So I've got, coming into node A, I've got I sub test. Right, so I've got I sub test coming in. I got I sub x coming out right here. I've got 3 I sub x coming out here. And I've got to choose something coming out here. And last time I chose this current direction, but just to show you that it's really a guess. Excuse me. So I'm just going to guess this way. And if I do that, I need an expression for this current. And I can get it in terms of Ohm's law because there's this resistor, this 2 ohm resistor is across V sub t. Do you see that? Do you see? This is just a big node right here, and then you've got this resistor, and then you're coming all the way back on node B. I mean, all along the bottom here, I mean, is node B. You could even label this node B. Right? So this 2 ohm resistor is really, it's across AB. So this current, basically, by Ohm's law, is going to be VT over 2. So that's coming out. So it's negative VT over 2. Those sum to 0. Did I get them all? I got I sub t coming in. I've got I sub x coming out, so it's negative. I've got 3ix coming out, and then I've got v sub t over 2 coming out. That's it. This expression has 3 variables in it. It has I sub t, I sub x, and v sub t. We can get rid of I sub x because we can express I sub x in terms of Ohm's law, because I sub x is also across nodes A and B. So likewise, I sub x has, we could express as v sub t over this resistor 8 ohms, v sub t over 8. So I sub x equals v sub t over 8. You can plug that in here, and you're going to get I sub t minus, let's factor the 4. And you get that. And this guy here has 2 variables, Vt over It. And we're looking for an expression in terms of Vt over It's. And that'll give us R sub Thevenin. So what I'm saying is we don't actually need the Vt value and the It value. We just need this ratio here. We just need Vt over It. Okay, so we can get that out of here algebraically. That's the trick. So I'm going to solve for that. So what I'm doing here is I'm solve for Vt over It, which will give us R sub Thevenin. Okay, so It equals, let's move these guys to the other side, is going to be 4 Vt over 8 plus Vt over 2, and 4 over 8 is Vt over 2 plus Vt over 2, this Vt over 2 over there. That's going to give you, it's just Vt. So, therefore, Vt over It is 1, which is R sub Thevenin. Okay? Was that fun? So the answer is the Thevenin equivalent, which we are seeking. We solved for V sub Thevenin a while back, seems like ages ago, but that turned out to be 8 volts. And this guy is R sub Thevenin is 1 ohm. This is our Thevenin equivalent. All right? Thanks. Bye-bye.